All right, I'm pleased to announce that the next paper has received a Best Paper award. The paper is Non-delusional Q-learning and value iteration. And the authors are Tyler Liu, Dale Shermans, Craig Boutillier. And here's your award. Congratulations.
All right, thank you very much.
Thank you. And the other two authors are modestly sitting down.
Yeah. All right, hi everyone. I'm Tyler Liu, and today I'll be talking about a new phenomenon which arises in value-based reinforcement learning with function approximation. We call it delusional bias, and it can cause some significant problems for value-based RL. We'll also outline some new algorithms and analysis we've developed to tackle this problem. So we've seen some tremendous success with deep RL in recent years in a variety of domains. And Q-learning has played a crucial role in many of these successes. In fact, it is one of RL's foundational algorithms. But Q-learning with any sort of function approximation, including deep Q-learning, is known to be brittle and can be difficult to make it work well in practice for a variety of reasons. As a result, there's a whole industry devoted to the creation of new algorithms, training techniques, modeling tweaks to address some of these problems. And today I got some even more bad news for you. This may sound surprising, but there are still fundamental issues lurking within value-based RL that have gone unnoticed after all these years. In this work, we present a new type of problem called delusional bias, which arises for two reasons. First, function approximator, we're inherently restricting the class of realizable greedy policies that we can execute. Second, classical algorithms like value iteration and Q-learning perform Bellman backups independently at each state action pair, completely ignoring this policy class restriction. As a result, as we'll see, the interaction of these two aspects can really cause a lot of headaches. But we do have some good news. We developed two new algorithms which completely resolve delusional bias with general optimality guarantees. The first is in the model-based setting, which we call policy class value iteration. The second in the model-free setting, which we call policy class Q-learning. So what is delusional bias? Well, let's start off with a simple observation that doesn't get the attention it deserves within RL. When we learn a Q function using our favorite algorithm, we typically act greedily according to that Q function. This means that with a restricted approximator class, we inherently limit the class of greedy executable policies. To illustrate this, consider this simple MDP, where action D in state 3 gives you small reward, action C randomly transitions you to one of two states, and action A and B gives you either a high or low reward with the parity flipped at the two states. It's easy to see that the optimal policy takes action C, and if you end up in state 1, take A, and if you end up in state 2, take B. This gives you a value of 50. Now suppose that we want to use a linear function approximation. And suppose we have the following featureization. Don't worry about the details. They aren't critical. Well, it turns out that there's no set of parameter values that would assign a higher Q value to action A in state 1 compared to B. And yet, at the same time, we'll assign a lower Q value to action A in state 2 compared to B. That is, there's no greedy policy that can execute A in one state and B at the other. This means that all greedy policies have to execute A in both states or B in both states. So it's easy to see here that the optimal greedy policy takes action C and takes action A wherever you end up. This gives a value of 40, which is slightly below that of the optimal policy. So what could go wrong here? Well, suppose we apply Q-learning to this example. And suppose that we sample all the transitions roughly uniformly. Due to the nature of the approximator, if we increase A's value in state 1, we also increase it in state 2. And we push down B's value in both states. And likewise, if we increase B's value in one state, we increase it at the other, and we push down A's value in both states. Well, it's easy to see that this tension causes the stochastic approximation nature of Q-learning to converge to a compromise value for actions A and B with a Q value of 0. This implies that action C also gets a Q value of 0. As a result, Q-learning sees that action D is slightly better with a slightly higher reward. And it converges to a greedy policy that has a value of 1. This is much worse than the greedy optimal policy in the class of representable policies. So what happened here? Well, because the Q backups have no idea whether certain action combinations are jointly feasible, Q-learning is perfectly happy to average together values that are not jointly realizable. In this case, Q-learning deludes itself into thinking that it can average together values of A and B to get a value of 0. As a result, it converges to a greedy policy that is much worse than the optimal greedy policy available in the representable class. So how do we prevent this from happening? Well, notice that whenever we make a max action choice to generate a Q label, we're implicitly making a policy commitment which justifies that Q label. But whenever we make a max action choice at one state, it may conflict with another max action choice at another state. Like in our example, we cannot do A and B in states 1 and 2. So as a result, in some cases, we may need to compromise and select action choices to generate the Q labels, which are non-maximal. To do this, we need to do two things. First, for each Q value estimate, we need to record the set of policy commitments which justify that Q value. We organize this into what we call information sets, and critically, we need the ability to test whether the policy commitments within an information set is consistent with respect to the greedy policy class. Second, because we don't know a priori which policy commitments might conflict with one another, we need to maintain multiple information sets, each with its own value estimates. So it's best to illustrate this on a running example where we do it in the style of value iteration. So consider the backup in state 2. Normally, we notice that B has a higher value than A, and we associate with state 2 a max value of 50. But because we don't know how the choice of B will interact with max action choices at other states, we also need to record the value of doing A. So in this case, we end up getting two distinct information sets, each with its own different policy commitments and its own Q values. We do a similar backup in state 1, and we get two distinct information sets, each with its own policy commitments and its Q values. Things get interesting when we back up action C for state 3. Normally, we just take an expected value over the successor states. But since we no longer have a single successor state value, we actually need to consider the different possible combination of the information sets or the policy commitments available in states 1 and 2. That is, we actually need to back up entire information sets and not just the Q values. So for example, if we commit to doing A in both states, along with the choice of C in state 3, then we get a new information set with a value of 40. Likewise, if we consider committing to action B in both states, we get a refined information set with a value of -40. Now, we might consider doing A in state 1 and B in state 2, but before we even consider that combination, we have to do a feasibility check. And we realize that there's no greedy policy that can execute those combination of action. Therefore, this set must be pruned. Similarly, we can't do B in state 1 and A in state 2, and we must prune this potential information set. And then finally, we do a simple backup for action D. Now we're ready to extract the greedy optimal policy. We do a simple lookup here, and we see that the greedy optimal policy has value 40, given initial state of state 3. And the policy commitments tell us exactly how this greedy policy looks like. We'll notice that at each state, the information sets form a complete partition of the value function parameter space, or equivalently the policy space. Now, you might also be concerned about the proliferation of the information sets, but it turns out that this pruning is exactly what's needed to keep things tractable. Now, it's easy to turn this intuition into an algorithm in a model-based setting, which we call policy class value iteration. And in a model-free setting, we just need to do sample-based backup instead to get policy class Q-learning. So what can we say about these algorithms? Well, I'll refer you to the paper for more details. But roughly speaking, we can show the following. First, both PCVI and PCQL converge, and they both converge with respect to the information sets and the Q values contained in those sets. Second, at convergence, we can easily extract the greedy optimal policy and its true value. And furthermore, the information sets and the Q values themselves are non-delusional. And lastly, you might be concerned about the proliferation of the information sets, but the number of them and the number of feasibility checks is actually polynomial in the size of the MDP. They do depend on the VC dimension of the approximator class, but for fixed architecture, we have polytime bounds. As a corollary, for fixed dimensional linear function approximator, PCVI is polytime. So the foundations are pretty solid. But what can we say about its performance in practice? Well, it remains to be seen for larger scale problems. But in some cases, being non-delusional can have a dramatic impact. So we ran our algorithms on some simple grid-world domains, and grid-world can actually be very hard if you have randomly generated features with linear function approximation. So this is a set of results on a 5x5 grid world with sparse rewards at the corners of the grid world. You can see at the top of the plot that the unconstrained tabular Q-learning and value iteration converges to the optimal value estimates. This is as expected. Just below that, we see PCVI and PCQL. With linear function approximation, we can't expect them to converge to the optimal value estimates, but we see that it very quickly converges to the constrained value estimates. And even quicker, it converges to the greedy optimal policies. By contrast, as we see in the bottom of the plot, by not accounting for delusion, both Q-learning and value iteration with the same approximator class fails miserably. In fact, its induced policies is so bad that they accrue effectively zero reward. So let me summarize by making a couple of key points. First, we believe that delusion is an overlooked but quite important phenomenon that need to be added to the catalog of RL problems. It can cause some significant consequences, including poor value approximation, and as we show in the paper, it can cause a host of other pathological behaviors that are undesirable. We propose new value-based RL algorithms which directly tackle the foundations of this problem, although they are not currently scalable in their current form. But this raises a number of interesting future directions. How do we incorporate concepts like information sets with large-scale Q regression? And we prefer some initial experiments on larger domains with linear function approximation, and the results look quite promising. But there's still a lot to do here. Second, how prevalent is delusion in practice? Well, based on our preliminary experimental results, as well as arguments with respect to VC dimension on the size of the greedy policy class, we suspect that this is quite prevalent in practice. Third, how do we do efficient feasibility checking with large-scale DNNs? And lastly, we view our methods in some sense as bringing together value and policy-based RL in a very interesting way. And we'd like to explore that connection more deeply as well. So with that, I'll conclude. And if you'd like to chat more about this, please come to my poster session tonight. And yeah, questions?
Thank you. Great. We've got time for a couple of questions. Ian?
Hi. Thanks a lot. Really cool work. But I guess I didn't see the point in, we see that delusion can be a problem, and one solution is to keep track of these information sets. Right. Another solution is to make your function class more flexible. And so that seems like the more obvious solution, and it could actually lead to a better optimal performance. So everybody could speak about that.
Thanks. That's a very great question. So usually we think about this as, you fix your function approximator class ahead of time, right? Whether it's neural networks or something else. And it doesn't matter what function class you consider, the VC dimension is the key indicator. So even if you have a very large neural network, right, the VC dimension is fixed. And depending on how large the problem is, the number of greedy policies is still much less. In fact, polynomial in the size of state space compared to the number of unrestricted mappings from states to actions, which is exponential in the number of states. So, those are two very differing policy classes. So we suspect that, the interaction of the greedy policies as well as the value estimates and the Q backups will still, cause delusion.
I have a question. Wouldn't an actor-critic algorithm resolve this problem automatically? Because then you would be evaluating only policies that can be expressed by the functional approximator. So any actor-critic algorithm, can you comment on that?
Yeah, so I think in general, with on-policy methods, if you're purely on-policy, then you're non-delusional. You're going to be non-delusional. But as soon as you try some type of policy improvement method, you're having to evaluate, what the off policy or what a potential improving action is. And so when that happens, you need to make sure that the actions you're considering are consistent with respect to your underlying greedy policy class. So there's still that potential for delusion to creep in that case.
But actor-critic algorithms can also be off policy as well.
Sorry?
I mean, actor-critic algorithms can also be off policy.
Yeah.
As well, I think it would just resolve it automatically.
Well, okay. So maybe we can talk about that more offline. So,
yeah. Hi. I'm wondering how this compares to like in the context of the problems that we already knew exist with like function approximation, like the deadly triad and stuff, and like I forget what it's called, but there's this two-state MDP, this classic like counterexample to function approximation. So can you like contextualize it against these previously known problems?
Yeah, so that's a great question. So we show in the paper also that divergence is in the example of that two-state MDP as you discussed, can also occur with delusion. So if you remove the delusion, it turns out that the example in the paper, in fact, converges. So there are other issues. For example, bootstrapping, which can cause a host of problems as well, which we don't really address in this work. So some of those aspects about the three deadly triads is kind of orthogonal to what we're doing, but delusion you can think of as sort of a new phenomenon that arises because of the greedy policy class and the queue backups, which don't respect that greedy policy class, and it can cause issues like divergence as well. So, yeah.
Okay, thanks.
Just one quick question while we switch out the computers, and then we'll stop.
Yes, I have a very quick question. Is delusion happens when the optimal policy is realizable by your function approximation, or in that case we don't have any delusion?
No, it could still happen. So even if the optimal policy is within the class of greedy representable policies, it could still be that your averaging values were corresponding to a combination of actions at particular states, which are not feasible. So you're wasting the capacity of your function approximator to fit those value estimates. So this phenomenon still occurs. It doesn't matter whether the unrestricted optimal policy lies within your greedy class or not. Yeah.
All right, let's thank Tyler again. Thank you. The laptop's down there. Nope.